So let's see if we can estimate how a neutron star rearranging itself might be a gamma ray burst and how far it would be. So we know that gamma ray bursts have a fluence, that is how much energy is received here on Earth within a piece of Earth of a given area, of about 10 to the minus 7 joules per meter squared. And we know a neutron star has a radius of about 10 kilometers, which is equal to 10 to the 4 meters, and a mass of about 1.4 times that of the Sun, and that is equal to 1.4 times 2 times 10 to the 30 kilograms, or about 2.8 times 10 to the 30 kilograms. So we're just going to rearrange a neutron star by, let's just say, 1 part in 10 to the minus 4. 1 part in 10 to the 4, or by 1/10,000th. So imagine that we want to figure out how much energy that might release. So what we're going to do is we're going to move 10 to the minus 4 of the mass of the neutron star, and we're going to move it by 10 to the minus 4 of the radius of the neutron star. And if I do that on Earth, I know that the energy, the potential energy change, is equal to the mass times the gravitational acceleration of the Earth, g, times the height. Now, the gravitational acceleration of a neutron star is not the gravitational acceleration of the Earth, so we're going to have to calculate it, and we use Newton's laws to figure out the gravitational acceleration of a neutron star. And in the same way that we would calculate that for Earth, we know that the gravitational acceleration of a body is gm over its radius squared. And so if we plug our numbers in for a neutron star, we find that g is 6.67 times 10 to the minus 11 in SI units. The mass of the neutron star is 2.8 times 10 to the 30 kilograms. And the radius is 10 to the 4 meters. We have to square it. So if we simplify that down, we're going to call that 6.67 times 2 is a little bit less than 6.67 times 2.8. It's a little less than 7 times 3, so we'll call that 20. And I have, using my exponential notation, 10 to the 19 on top, 10 to the 8th on the bottom. And so altogether, that gives us about 2 times 10 to the 12 meters per second squared. That's a lot more than the 9.8 meters per second squared we have on Earth. So that means that the change in energy is going to be equal to m, which we decided is 10 to the minus 4 times the neutron star. So 10 to the minus 4 times 2.8 times 10 to the 30 times the height, which is 1 meter, times g, which we've just calculated as being 2 times 10 to the 12 meters per second squared. So simplifying that all together, we can knock that down to essentially 3 times 2 is 6. And then consolidating my exponential notation, I have 30 plus 12 is 42, minus 4 is 38. So 6 times 10 to the 38 joules. Now we know that the fluence is going to be equal to the energy of the object divided by 4 pi times the distance squared. Or in other words, the distance is equal to the square root of the energy divided by 4 pi times the fluence. So if we have an object that puts out this much energy, and it has this fluence, we can calculate its distance as being its energy, which we've just calculated as 6 times 10 to the 38 joules, divided by 4 pi, which I'm going to call 12. 4 pi is roughly 12, times the fluence, which is 10 to the minus 7. And that's all to the 1/2 power. So 6 divided by 12 is a half, and 38 plus 7 is 10 to the 45. In other words, I have essentially 5 times 10 to the 44 to the half power, and that is equal to square root of 5 is about 2 times 10 to the 22 meters. Now, 1 megaparsec is equal to 3 times 10 to the 22 meters. So this is about 2/3 of a megaparsec, or the edge of our galaxy. So now let's try this for something perhaps much more energetic, a black hole. A black hole of, for example, 10 solar masses, which is 2 times 10 to the 31 kilograms. And we're going to take it from being very large, so essentially a radius which we'll call infinity. I'm going to shrink it down to the radius of a black hole. Now you may remember that the radius of a black hole, or given as the Schwarzschild radius of the event horizon, is 2gm over c squared. So I want to find the change of potential energy. Now we know from Newton's laws that the potential energy is equal to gm little m over r for an object attracted to another object. So I'm going to pretend that a star's potential energy can be described as half the mass being attracted by the other half of the mass. So half the mass sitting on top of the other half. So that means my big M and my little m here are the same. They're both half of big M. So I'll get G 1/2 m times 1/2 m divided by r, which is equal to G over 4rm squared. So that's the total potential energy of a sphere of mass m. Well, it turns out it's an approximation because I've sort of put half the star on top of the other half. The formal calculation tells you that the real answer is 3/5 m squared over r, potential energy of a sphere, of a uniform sphere. So I have a sphere that's very large radius, so it has 0 potential energy, shrinking down to the radius of a black hole. So the change in potential energy is simply going to be this expression we've derived for the potential energy, because it goes from 0 to this new value, with the radius substituted in with the radius of a black hole. So the change in potential energy will then be 3/5 m squared, where I have now taken the radius and replaced it with 2gm over c squared. And that gives me now 3 over 10 times m c squared, or 30% of the rest mass energy. So if we put that number in for the relevant values of a black hole, I get 3 over 10 times 2 times 10 to the 31 kilograms times c squared, which is 3 times 10 to the 8 meters per second, whole quantity squared. And so, again, making some approximations, I've got 3 over 10. I've got that 2 times 10 to the 31. And I have 9 times 10 to the 16 once I square. So 3 times 2 times 9 is 54, so we'll call it 50 divided by 10 is 5. So I get 5 times 10 to the 47 joules. So it's a lot of joules released. And using the same formula that we had before, given the fluence that we observe for an object, we can estimate that the distance to these things is going to be equal to the square root of the energy, which is 5 times 10 to the 47, divided by 4 pi times the fluence, which is 10 to the minus 7. So the distance could be calculated. 5 divided by 12 is roughly a half. So I have the square root of a half times 10 to the 54, which equals the square root of a half is about 0.7 times 10 to the half of 54 is 27 meters. So given that 1 megaparsec is equal to 3 times 10 to the 22 meters, this corresponds to 2 times 10 to the 4 megaparsecs. And that is the edge of the universe.